Welcome to today's lecture covering the accuracy of averages. The object of this chapter is to estimate the accuracy of an average computed from a simple random sample. This section deals with a preliminary question: how much chance variability is there in an average, in the average of numbers drawn from a box? We know already that the sum of the draws is subject to chance variability. And because the average is just an extension of the sum, it's also subject to that same chance variability. So the new focus, the new problem in this chapter, is to learn to calculate the expected value and standard error for now the average of the draws. And we will look at this method through an example. Here we have an example with 25 draws made at random with replacement from this box where each number 1 through 7 is represented one time. And we need to find the average of the draws. This is going to be, we already know generally that this is going to be around the expected value of the average, give or take a standard error. But now we need to just extend this same idea we've been doing this whole unit now to looking at averages. Oops. With that in mind, we'll do a nice example here. There are several terms that we're going to need. The first is our target term. This isn't the first term we'll calculate, but the first term that I know we're going to need is that we just said is the expected value of the average. We're also going to need the standard error of the average. We'll get there vis-a-vis a pathway through the mean of the box, the expected value of the box, sum, not the expected value of the box, the expected value of the sum, excuse me. And the standard error of the sum. Note that most of these terms are familiar to us. With these two target terms are new, but we're just going down a familiar path. First thing we know we're going to need in order to find our expected value is the average of the box. This is generally our first step in a lot of these problems. And the average of the box, we're also going to need the standard deviation of the box, which I'm going to give to you because this is not a shortcut standard deviation. We would have to actually get, to get this standard deviation, we would take the mean of the box, which is 4. We just get that by computing the mean of this box, add the numbers, divide by 7. And the SD of the box, we could get through our standard formula for the standard deviation. The sum of the mean, or x, excuse me, minus x bar divided by n, all under the radical. But we are going to take a shortcut here, which is that I'm giving you the standard deviation of the box rather than because we already know how to do this formula, and it's not the primary focus right now. It's 2. So let's collect our terms over here. The mean of the box is 4. Standard deviation is 2. Well, excellent. Now we're ready to get the expected value of the box, or of the sum, excuse me. Oh, what am I talking about? We need to get the standard error of the sum. No. Sorry, remember my notes are covered in, I'm gonna have to wing this because everything is wet right now. That's fine. The expected value for the sum, as we know, is the number of draws, 25 draws, times the average of the box. The average of the box is 4. So the expected value of the sum is 100. If the SD of the box is 2, then the standard error for the sum is, as always, the square root of the n for draws times the SD, or the square root of 100 times 2. So it's 10. Wow, look at us making our way through this problem so efficiently. So this is all very familiar, right? And we know that the sum of the box for these 25 draws will be about 100, give or take 10 or so. But what does this tell us about the average of the box? Or the average of the draws, excuse me. The average of the box is 4. If the sum is 1 standard error, I'm just going to do a shortcut here. So the average of the draw of our 25 draws is going to just be simply the sum of the expected value of our sum, 100, we'll take the expected value of our sum and divide by the number of draws. And that's 100 divided by 25. So this bit is 4, but we need the give or take piece, which is the standard error for the average. Oops. And we know that the standard error for the average is like the standard error for the sum divided by the number of draws. So nothing shocking here. 10b20. Did I sum the expected value of the sum? Oh, I see. I'd made a. You're right, but I keep doing this today. I wrote in the wrong number here in the standard error calculation, like when I was writing this out, but then I wrote the right answer there. It's a very good catch, Molly. So the number of draws this time is 25. We earlier did problems with 100 draws. Anyway, the number of draws is 25. And the square root of 25 is 5, times 2 is 10. So I'm very glad you caught that because, I mean, the answer was right, but the math there. This is a great example of another common pathway to error that I see. Not just, I'm not unique. Students do this all the time. You're writing out all these numbers. We just wrote 100 and I ended up writing 100 down here again. Oftentimes when there's an error in calculations, it's in something like that, where the wrong number was written. For example, it's a small error, like not a big conceptual one. The correct math was done, but maybe the wrong value was put in. It's a very common error. So just another tip when you're, checking over your answers. And we'll remember now that our number of draws is 25. And so the standard error of the average is 10 out of 25, or 0.4. So we know that the average of the draws will be around 4, give or take 0.4 or so. So as you can see, to find the standard error for the average of the draws, you just go back and get the standard error for the sum and then divide by the number of draws. The standard error for the average, let's look at this as a formula. When you're drawing at random from a box, remember this only applies to a simple random sample. The expected value for the average of draws is just the average of the box. But the standard error for the average of the draws is the standard error for the sum divided by the number of draws. So this is another slightly different standard error, and in a little bit we'll look at all of our standard errors and think about when to use them. The standard error for the averages, this one, says how far the average of the draws is likely to be from the average of the box. Let's see. Oh, so here we have our, we'll take a quick look at these probability histograms. And the point is that The top one here is the probability histogram for the sum of draws from the box, and the bottom panel shows us the probability histogram for the average of the draws. As you can see, in standard units, the histograms are exactly the same. They differ in their absolute values, but in standard units, our second line, they're exactly the same. So we're really just doing a small add-on to what we were previously doing before. The division, when we move from the sum of draws to the average of draws, we just are taking our sum and dividing by the number of cases or draws in our sample. And this division is just a change of scale. That's the main point to take home here. When we move between these two, we're just changing the scale. And that washes out in the standard units. So that in standard units, they're the same. And they both follow the normal curve. Now let's think about our sample average. There's two primary questions to answer. First, what's the difference between the standard deviation of the sample and the standard error for the sample average? This is a great question. The standard deviation is a simple is computed simply from a list of data. So it doesn't it doesn't give us all the information that we need in terms of the standard error and there's distinctions in how we can use them. So we can take our standard error and make inferences to the population, but with the standard deviation, that's not possible. The standard error is for a variable, where the standard deviation is just for a list of data. With a simple random sample, the standard error of the average is estimated by substituting the standard deviation of the sample for the unknown standard deviation of the box. Then confidence intervals are obtained by going the right number of standard errors either way from the average of the sample. Because we need a standard error to account for our sample sizes. So let's think about confidence intervals for a minute. With a large sample, we can often get a probability histogram that resembles a normal curve. And it's okay to use the normal curve in figuring out confidence levels when we can, when we've used the simple random sample process and our variable resembles a normal distribution. The why here is a bit mathematical. I think what we're getting into, I guess, in these questions is a bit more mathematical logic than I think we need to go into. The standard deviation Strictly speaking, the standard deviation is you can find for any list of data. Like we get the standard deviation of just the box. We don't need to know a number of samples. The standard deviation is just for the list of the data in the box. But the standard error gives us helps us account for variability in terms of the sample size, because the expected variability from the average changes based on the sample size. So the SE is for a variable, and the standard deviation is just for the box. It's a subtle point. The standard error is used in inference, but it doesn't do inference itself. The big question that we really need to take home from today's discussion is which standard error to use when. Regardless of which standard error we're talking about, it shows us the likely size of the amount off. It's always a give or take number. And we can get it by sometimes we have two scenarios basically. We are sometimes reasoning forward, where we know the box, we know the composition of the box going in. So the standard error can be computed exactly from the composition of the box. Other times, we're reasoning backward, where we estimate the standard deviation of the box from the sample. And in this case, when we're reasoning backward like that, the standard error is only approximate. And the standard error you need to use depends on the goal of the type of answer you're looking for. As we know, some of these are linked. You know, the standard error for the sum, you're going to obtain en route to getting the standard error for the average. We'll also use the standard error for the sum when we get the standard error for the count. And so we really end up using these standard errors in different forms and sometimes embedded in each other. This is the simplest and most easiest to manage terminology for managing these different types of standard errors. I know it seems repetitive, but trust me, the other ways to manage this terminology you'd find even less palatable. I'll just leave it there. Let's think about, like, reasoning forward is easy to imagine. We did a lot of this already where we compute directly from the composition of the box. This idea of reasoning backwards from our sample and then inferring about the box, that's a newer idea. And when you're reasoning backward from the box, you often have to estimate the standard deviation of the box based on the sample. So in this case, our standard error is only an approximation, but the interpretation of the standard error is still almost the same as in our other scenarios. For instance, if you suppose that the average of the sample is used to estimate the average of the box, this estimate will be off by a little, and the standard error tells us about how much. When the sample is reasonably large, then the error in the standard error is usually too small to matter. So even though we are estimating the standard error, if it's a sufficiently large sample, that little bit of estimation error isn't going to cause us a problem. The confidence interval is just an application of the standard error, where we use the standard error to compute a range from the sample, and the range covers the population average with some specified degree of confidence, usually 95%. Let's take one final look at sampling and think about how some of these how important it is to keep in mind some of this information about sampling. A simple random sample is needed for a valid evaluation of the accuracy of an average. We always need that simple random sample. In terms of these issues, the accuracy of the average, and we can't apply this statistic validly unless we have a simple random sample. Of course, you could compute it. Mathematics will not protect you from an error in logic. And so what I'm talking about here is methodological logic, where you need to remember to think about the methods, not just the numbers. Remember, statistics is not just numbers. It's very much about the methods and the conceptual understanding of when to use those numbers and where. If the data don't come from the right kind of sample, the result of the calculation might be nonsense. And so that's why you just can't, mathematics isn't going to protect you. Oftentimes, we encounter a sample of convenience, which is not taken by a probability method. A sample of convenience is often used. Lots of professors will do research on their students. Well, that's not a random sample because they're students who are taking that class. It doesn't stop us from doing research, and there are certainly other methods that we can use when we don't have a simple random sample. But a simple random sample technique is the foundation of a lot of good statistical good methodology and resultant statistics. With a convenience sample, the standard errors generally don't make sense. And oops, what happened there? Oh, and now we are at this point in our study of statistics, starting to make a transition from probability calculations to inference, especially in this chapter today. First, we distinguished sampling error from non-sampling error and looked at how important it is to have a chance process in our sampling methodology or random sampling, that using the probability methods to help us draw a sample in a way that we can use statistically appropriately. Then we developed the theory behind a simple random sample, learned how to estimate the population percentages from a sample percentage. This is our first foray into doing inference. And then we make the transition to looking at averages, which are the most common way to report summary statistics. So this has given us a nice overview and launching point for our next unit on formal inferential statistics or tests of significance. And just as researchers always hope for, may the odds be ever in your favor.